Hello, my name is Mitchell Conover. Today I'm going to be discussing the results of a methodological study evaluating the performance of Austin's standardized difference heuristic in observational cohort studies with varying sample sizes. This work represents the combined efforts of Azza Shoaibi, Joshua Ide, Martijn Schuemie, and myself in collaboration with the OHDSI PLE-PLP working group. All authors are employees of Janssen Research and Development. A common approach to assessing the potential for confounding by measured covariates in observational causal studies is to compare the distribution of covariates among the exposed and the unexposed. An informal but long-standing practice is to require that the standardized differences between the comparators be less than 0.1. This applies to studies that balance using exposure side adjustments such as propensity score methods. The use of 0.1 as a cut point for standardized differences was developed and applied during an era of observational research that considered small, manually curated sets of suspected confounders. However, increasing use of large-scale high-dimensional adjustment approaches mean that researchers now consider large covariate sets, which can include hundreds of variables. In this context, requiring all variables to be balanced with a standardized difference below 0.1 might be unnecessarily conservative. Particularly in studies with small samples, chance imbalances that do not reflect problematic confounding might be particularly likely. Thus, we sought to investigate the performance of Austin's absolute standardized mean difference statistic to identify problematic confounding in studies estimating causal effects. We conducted this assessment in analyses of various sample sizes, which used propensity score matching to adjust for a highly dimensional set of covariates. Our assessment looked at two previously investigated clinical settings looking at antihypertensive treatments. We compared ACE inhibitors versus thiazides and thiazide-like diuretics, a comparison which we expect to show minimal confounding, and also a comparison of ACE inhibitors and beta blockers, which is a comparison we expect to show more confounding. To evaluate the heuristics' ability to accurately identify confounding, we looked at analyses that passed or failed diagnostics being assessed, all of the covariates having a standardized mean difference below 0.1, and we summarized the expected bias by means of the negative control distribution. We considered 4 large secondary health databases that include national samples of patients. We looked at 3 claims databases, including Optum Clinformatics Extended Data Mart, IBM MarketScan's Commercial Claims and Encounters database, and IBM MarketScan's Medicare Supplemental database, which includes older patients. We also looked at Optum's de-identified electronic health records database. Within each of these databases, we selected cohorts of patients at the point of their first observation of exposure to either the target or the comparator drug. We defined cohort exit as the earliest occurrence of the outcome event, the exposure discontinuation, death, disenrollment from the database, or the date of last data collection. We applied 3 inclusion rules to each cohort, including that the patients were adults, that they had at least 1 hypertension diagnosis preceding their initiation, and at least 365 days of continuous enrollment in the database before cohort entry. We considered a large set of causal effect estimates, which correspond to 76 negative control outcomes. Negative control outcomes are those that we are confident have no causal relationship with the antihypertensive exposures being studied. In analyses with minimal systematic bias, we expect that the effect estimates should tightly cluster around the null, with an approximately normal distribution, as shown in the figure on the right. The empirical null distribution indicates bias due to uncontrolled confounding, which may result from imbalance in either measured or unmeasured covariates. To understand the performance of Austin's standardized difference heuristic in studies of varying sample sizes, we separately analyzed subsamples from the original target and comparator cohorts. We looked at 5 20% samples, 10 10% samples, 25% samples, and 101% samples. Austin's standardized difference heuristic was used to identify problematic covariate imbalance within 3 separate analytic scenarios. First, we looked at a crude analysis with no adjustment for confounding. Second, we looked at a 1-to-1 propensity score matched analysis. And finally, we looked at an analysis using a simulated exposure variable that should be equivalent to randomization. We estimated propensity scores using data-driven, large-scale regularized logistic regression. Estimates of the propensity score used to adjust the comparisons were modeled in the full pooled cohort, and one-to-one matching procedures were applied within each of the population subsamples. We used Cox proportional hazards models to estimate the hazard ratios between the target and comparator treatment cohorts for the risk of each negative control outcome. Hazard ratios and empirical null distributions were generated within the combined cohort, which combines either the crude or the matched populations produced in each subsample. For each analysis, we summarized the following statistics separately for dichotomous and continuous covariates. We looked at the mean standardized difference across all covariates. We looked at the maximum standardized difference across all covariates. And we looked at the proportion of the covariates that had a standardized difference greater than 0.1. The expected systematic error and 95% confidence intervals around it provided a quantitative summary of the negative control distribution. A higher value of the ESE indicates increased systematic bias, including residual confounding. Uncertainty in the empirical distribution parameters in the ESE were quantified using Markov chain Monte Carlo iterations and expressed as 95% credible intervals. Here we show the results of our analyses for the Optum-DoD claims database for the comparison of ACE inhibitors versus beta blockers. As you can see, we have a two-paneled graph. Along the x-axis of both graphs, we show the proportion of the source populations that were subsampled. In the top graph, the y-axis indicates various statistics reflecting the standardized difference. The dotted lines show the standardized difference for the most imbalanced covariate, where the solid line indicates the average standardized difference across all covariates. In the bottom graph, we show the corresponding estimates of the ESE, which indicates the suspected systematic bias. The crude approach failed the diagnostic, in other words, had at least one covariate with standardized mean difference greater than 0.1 for both comparisons in all databases for all subsamples considered. In Optum-DoD, across all subsamples, the average of the maximum standardized mean difference for the crude approach was approximately 0.63, which is not shown in this graph. The propensity score matched approach, which is shown in green, passed the diagnostic for larger samples, but failed at subsamples less than or equal to 5%. Of all of the covariates considered for both the crude and the propensity score matched approaches, the proportion with standardized differences greater than 0.1 was relatively stable for subsamples between 5 and 20%, increased slightly for samples at 2%, and increased substantially for samples at 1%. Despite the changes in the standardized mean difference diagnostics at lower sample sizes, as you can see in the bottom panel, the ESE statistic did not indicate any meaningful change in the systematic error or the ability of the propensity score matching approach to generate unconfounded estimates. For the crude beta blocker comparison, the ESE was approximately 0.25 across all subsamples and approximately 0.01 for the pseudo-random approach. The ESE for the propensity score matched approach ranged between 0.02 and 0.03, indicating a relatively unconfounded adjusted estimate, nearly equivalent to the unconfounded pseudo-random approach. Furthermore, the confidence band around the propensity score matched estimate for the smallest sample of 1% contains the point estimate for the unconfounded pseudo-random approach. Here we show the corresponding results for the comparison of ACE inhibitors versus thiazides or thiazide-like diuretics. As we can see, the red line in the bottom panel was lowered compared to the beta blocker comparison, which indicates a less confounded crude estimate. However, the conclusions are the same in terms of the standardized difference indicating a problematic imbalance when sample sizes are low. In Optum-DoD across all subsamples, the average maximum standardized mean difference for the crude approach was approximately 0.77 for the thiazide comparison, which is not shown in the graph. These findings were consistent across both comparisons and across all of the databases included in our study. In closing, this study leverages the empirical null distribution to inform an improved understanding of how to use the standardized mean difference statistic to diagnose small sample studies with high dimensional sets of covariates. These results demonstrate a loss in specificity of Austin's standardized mean difference diagnostic for identifying problematic confounding. In other words, it's more likely to indicate problematic confounding for smaller sample studies, even when none exists. This motivates important future research, including testing other proposed approaches for diagnosing problematic or uncontrolled confounding and comparing them to the Austin approach, and also potentially using the empirical null distribution to develop an OHDSI approach for small sample studies. The protocol for this study is currently saved in the MS Teams channel, Covariate Balance in Small Exposure Cohorts, and you're welcome to contribute and provide feedback in the PLE-PLP working group sessions. Thank you so much and have a good day.